Hi, good day. So for today, we are going to talk about the independent samples t-test. The independent samples t-test, also known as unpaired samples t-test, is one of the ways on how we can find the significant difference between two different sets of data that came from independent samples. Take note that that is independent samples, unlike in paired samples t-test, which came from dependent samples. Now, independent samples t-test can only be used if the two data that we have are normally distributed. And therefore, independent samples t-test is a type of parametric test. Also, because in independent samples t-test, we assume that our two data are normally distributed, then the most appropriate level of measurement that we should use here is under the interval or ratio scale. To give you an example on how this independent samples t-test works, let's have here an example research entitled The Growth of Tomato in Fertilizers X and Y. Here in this research, we want to know which fertilizer is effective. Is it fertilizer X or fertilizer Y? Okay, and so, for us to be able to know which of the two fertilizers is more effective than the other, we set up here two different groups of tomato plants. The first group only experienced the fertilizer X, and the second group only experienced the fertilizer Y. Now, in each group, we have actually 5 tomato plants, so a total of 10 samples. So we have here 10 samples. Now, take note that our data here from fertilizer X is different from the data from our fertilizer Y. These two data here came from independent samples. Okay? They did not came from the same sets of plants, but they actually came from different sets or different groups of plant. Okay? So what we did here was we get first the total. Okay, we get first the total of their growth after 1.5 months. Okay, so we obtained their growth after 1.5 months. So we have here 90 centimeters, 82 centimeters, and so on and so forth for X fertilizer. And we have here 78 centimeters, 64 centimeters, and so on and so forth for the fertilizer Y. And then we obtained the total for for their growth or for the growth in fertilizer X and fertilizer Y. So for in fertilizer X, we have here 423 centimeters, and for fertilizer Y, we have here 342 centimeters in total. Also, we get the sample size for each group. For group X, or for the group that experienced the fertilizer X, we have here five tomato plants that experienced that fertilizer, and we also have here 5 tomato plants that experience only the fertilizer Y. Okay, so a total of 10 samples and 2 independent groups. Okay. Now, there are actually four things that we need to compute first before we go with the computation of the t statistics proper. Okay, so what are those four? We need to compute first the mean for the X, the mean growth for the X, next the mean growth for the Y, next the variance for the X, and the variance for the Y. Okay, now we already know how to compute the mean and the variance, so we are just going to apply what we learned in our past discussion. So here, our mean for X is equal to the summation of X over the N, or the sample size for X. In this case, the summation for all the X values here, okay, is 423. Okay, and our sample size here for X is 5. Okay, so 423 divided by 5, that is 84.6. So therefore, the mean growth for the tomato plants that only experience the fertilizer X is 84.6. Now for the Y, here, we have here the summation for Y, okay, divided by N. Our summation for Y is 342 divided by 5, which is our N for Y fertilizer. And we have here the mean growth for Y, and that is equivalent to 68.4. Now for the variance, we have here, okay, variance for X is equal to summation of quantity mean, okay, mean for X minus the individual data for X square over n, which is the sample size, minus 1. If we are going to do this or to substitute our values here from this equation, then we can have here variance for x is equal to 84.6, which is actually our mean, okay, minus the first data in our x column, and that is 90 centimeters square, plus 84.6 again, minus 82, the second data in our x column, square, plus 84.6 again, okay, minus 93, our third data, square, and so on and so forth. We're going to do that in our 5 data here, okay, divided by the n for x is 5 minus 1, okay, and that is 4. If we're going to simplify this equation, then we can have here 331.2 divided by 4. And if we're going to simplify further this equation, then we can have here variance for x is equal to 82.8. Okay. For y, we are also going to do that for y, but this time the mean here is the mean for y, and our data, our individual data here will now come from the y column. Okay, so we have here mean for y minus the individual data for y column square. So we are just going to do what we did in x, but this time in y column. Okay, and we will have here variance for y is equal to 48.8. Now, for the next things that we are going to do, we are going to determine the null hypothesis, the degrees of freedom, the alpha level or level of significance, the type of test, the critical value, and the decision rule. For the null hypothesis, our null hypothesis is there is no significant difference between the fertilizer X and fertilizer Y, or fertilizer X is just equal to fertilizer Y. For the degrees of freedom for independent samples t-test is equal to the sample size for x plus the sample size for y minus 2. Here, our sample size for x is 5. Our sample size for y is also 5. So 5 plus 5 is equal to 10 minus 2 is equal to 8. Therefore, our degrees of freedom is 8. For the alpha level, our alpha level again is always 0.05 or 5%. And for the type of test, we have here two-tailed because we did not mention any direction or comparative adjectives in our null hypothesis. We did not say x is greater than y or y is less than x. Okay, we did not say that. We are not sure on what will happen to our null hypothesis. So therefore, our type of test is two-tailed. Now, because our type of test here is two-tailed, what happened here in 5% is that we also divided this 5% into 2. So 5 divided by 2 is 2.5, and we located those 2.5% in the extreme portion of our normal distribution curve. That is on extreme left part of our normal distribution curve and on the extreme right part of our normal distribution curve. So if this is our normal distribution curve, we did not accumulate only the 5% in just one side of this normal distribution curve, but we divided them. We divided this 5% into two parts. The first part, okay, is located here on the extreme left part of the normal distribution curve, and the second 2.5% is located on the extreme right part of this normal distribution curve. Now, as we have noticed here, there is actually a clear line that separates. This is actually the clear line that I am talking about, this one and this one. Okay, there is a clear line that separates the rejection region and acceptance region. Now, the question is, what is the value of these clear lines here? Okay, what are the values of these clear lines here? So for us to be able to determine the values of this line that separates the acceptance region and rejection region, we need to determine our critical value for the independent sample, for this independent samples t-test. Now, to determine the critical value, there are actually three things that we need to identify first: the degrees of freedom, the alpha level or level of significance, and the type of test, which we already obtained earlier. Now, let's take a look at our critical value table or t-distribution table for independent samples t-test. This is our critical value table for t-test. Here, we know that our type of test is two-tailed, our alpha level is 0.05 or 5%, and our degrees of freedom is 8. By intersecting the value under 0.05 or 5% in two-tailed test and the value under 8 degrees of freedom, then we can say that our critical value or T-crit is 2.306. Now, after looking at the critical value table for independent sample t-test, we now know that our critical value is 2.306. That means these two lines here are represented by negative 2.306 and positive 2.306. Now, this one is negative because this line here is located at the left side of our normal distribution curve, and this one is positive because this line here is located at the right side of our normal distribution curve. And therefore, our decision rule here is if our computed t-value or if our t-com is less than or equal to negative t-crit, this is our negative t-crit or critical value for t. Okay? Or if our value falls under this region, okay, or greater than or equal to positive t-crit, this is our positive t-crit. Okay? Or if our value falls under this region, okay, we are going to end up rejecting our null hypothesis. Okay, so with those things now in our mind, let's now go to the proper computation for the t-value in independent samples t-test. So this is now the formula for the t-value. This is the formula for the t-value in independent samples t-test. T is equal to the mean for x minus the mean for y over the square root of the Vx here is variance for x over the sample size for x, how many tomato plants are there in x fertilizer, plus the variance for y over the sample size for y, how many tomato plants are there in fertilizer y. So by just substituting all the values that we obtained earlier, our mean for x here is again 84.6. So we have here 84.6. Our mean for y is 68.4. That's why we have here 68.4 over the square root of the variance for x in our computation earlier, that is 82.8. So we are just going to write 82.8 here over the sample size for x. The sample size for x is 5. So we are just going to write 5 here, plus the variance for y, which we already computed earlier, that's 48.8 over the sample size for y. Okay, sample size for y is also 5. Okay, so t by simplifying further this equation, then we can have here t is equal to 16.2 over square root of 26.26. Okay, and by simplifying further this equation, then we can have here 16.2 over 5.12, and 16.2 divided by 5.12 is positive t 3.16. Therefore, our t computed or our computed t value here is 3.16. Now let's have here the analysis. Our analysis here is that our t-crit is 2.306 as mentioned earlier, and our t-com here is 3.16. Okay, obviously, okay, our t computed is greater than the t-crit. Our t-crit is 2.306. Our computed t is 3.16. So t-com is greater than the t-crit. Our value for computed t lies under this region. And we know this region, right? This region is actually the rejection region. Therefore, we are going to reject our null hypothesis. What will be now our conclusion here? Our conclusion here is that there is a significant difference between the fertilizer X and fertilizer Y, or fertilizer X is not equal to fertilizer Y. So that's how we can actually use the independent samples t-test in finding the significant difference between two different sets of data that came from independent samples. So thank you for listening and good day.